Okay, let's take a look at this rock profile here. So imagine this is a valley. Maybe this is a creek running through a valley, somewhere like in the Chagrin River or the Rocky River or the Cuyahoga when you think of the flats, right? So when you're talking about stuff, places like that, this is really evident in the Rocky River as you go, if you ever get a chance to go walk the Rocky River Metro Parks. What you'll see is the rock strata, right? All the layers. Now around the Rocky River, there's just a lot of. So let's take a look at the bedrock of Ohio before we go on and looking at the rock strata. So if we look at the Chagrin, at the Rocky River go flowing through here. The Chagrin would be coming from over on the east side of the Cuyahoga. The Cuyahoga River kind of goes right through there. There's all kinds of rivers all go down and feed into Lake Erie. All of this area here, north of the high point in Ohio, all flow down to Lake Erie, where everything south of a certain point is going to flow down to the Ohio River, which kind of defines the southern border of Ohio. So when we take a look at the rock strata, so when I talk about bedrock, what you got to think about is that you're standing here and you have your trees that go into the soil there, right? And our houses and what have you are all here. And there's all kinds of soil layers. There's topsoil, there's loose gravel, and different layers and strata here. So if this is the root system of the tree. So this is soil and loose material, things that have been buried. At some point, underneath this surface, we're going to hit what's called the bedrock, the rock upon which all the soil and other materials that we're used to seeing sit on top of. That bedrock is different for every area, right? So in Canada, for instance, the bedrock is granite. In New York, in Manhattan, the bedrock is granite. Here in Ohio, we have a lot of shale and a lot of sedimentary rock. So when we look at this orange area where we live here in Cuyahoga, but this is the same for Lorain, all up and down this area, all the way down through here, and even here. This rock is of the Devonian period. That's how old the rock is. The rock just to our south is from the Mississippian era period, which is about 322 to 359 million years ago. Ours is older. It's 359 to 385 million years ago. So if you want to go all the way back to bedrock that's 510 million years ago, you have to go here as far south as Stark County or any of the counties down here. So as you know, when you're going down deeper, you're going to get, if you want to go to 1.2 billion years ago, you're going to go to areas that have this color rock or this color rock or even this color rock. So when we look at these, let's see, I'm not sure where I would see that. I guess you'd see it here. So if you want to look at bedrock that's that old, you'd have to come down here to this area of Ohio. But we are here at the Devonian period, which is, and specifically 359 to 385 million years ago. So this bedrock, the rock that's underneath all this loose stuff that we're used to seeing, is made of shale and siltstone. Now, shale is, it comes off as almost thin layers, and they break apart. I want to say brittle. But the shale looks something like this. Usually when I look at it, I see it's black, but I have a black background, so I'm going to draw it brown. And they kind of layers on top of one another. And it's all based on sediment. So it's sedimentary rock. So as sediment lays on at the bottom of a lake or river or ocean or what have you, all that gets compressed into these layers, almost like layers of an onion. So it ends up looking like this over time. This is the bedrock that's in most of our area here, in all of our area here in Cuyahoga County, and a good portion of Ohio. As you can see here, all this is this type of rock where it's all been sedimentary. It's all layered, it's turned into stone, but it breaks off. You see it breaks off as while the water erodes it, as weathers it, it breaks off and it makes these shelves. And then the shelves collapse and they make stones in rivers. And so what you'll see a lot of stone in the river. You'll see moss and algae growing on the side of river banks. You can see the high water mark would come all the way up to here. But these are the layers as the rivers cut through the bedrock. This is the layers of stone that have been made over time. And here's where we're going to find the fossils in these layers. And the deeper down you go, the deeper you dig, the older the rock, and you might even change the type of rock. In this case, it's shale or siltstone. You might dig down and find at some point granite. Now, remembering that the different stones, the different rocks, are made by different processes. So this is a sedimentary rock. So it's rock that's made from sedimentation, as sand and silt falls down at the bottom of a river or a lake. It makes it gets compressed into stone, and then later it could turn into soil, or maybe it stays at the bottom of a river or a lake. But what happens is over time, different creatures get stuck in the various layers and die and get petrified. They get turned into stone, but their impressions, their structure is saved in the fossil record. And so when we dig down and we look at these layers, we can find different fossils depending on what was alive during that period of time. And we assume that the deeper down you go, the older the rock. Now, as I said earlier in a previous short video, sometimes this isn't true. Sometimes these get flipped over. Sometimes there's breaks in the strata. Geologists can tell because they compare the rocks on one side to the other, and they can look and see evidence of the land flipping, or they match up the areas. For instance, you can see this type of rock, whatever it is going to be the same as this type of rock. So they assume that this area that's been carved out by a river or some other, maybe an earthquake pushed up magma, and here you have granite, let's say, or something like that, and something separated the land from this side to this side, right? So in the case of the Ohio Valley, it was carved out by a glacier. And then now you have the Cuyahoga River flowing through part of that valley. So the Ohio Valley was carved out by a glacier, and all that till was left over. And the till, I mean the glacier dug up the earth as it came south, and it left, as the glacier melted, it left all that here in the Ohio Valley, which is why the Ohio Valley is such a good place to grow things. They have a lot of nutrients from a long time ago. Maybe I think something like, I don't know how many thousands of years ago the last glacier came through the Ohio Valley. But the point is that it carved out the land. So you have the east side of the flats and you have the west side of the flats, and in the middle you have a river flowing through it. And if you were able to dig and look at the different layers of rock fairly deeply, you'd see that there's different kinds of rocks and different types of fossils found in each one. Now in D and L, you wouldn't expect to see any fossils because if you read, it says D and L are volcanic ash. So this was, in this example, was a volcano laid ash down. You wouldn't expect to see a fossil in this volcanic ash. I suppose You might, well, I guess it could, there could be a fossil in volcanic ash. You wouldn't expect to see it in granite, for instance, or marble, because those have been melted by magma and compressed and deformed. But in sedimentary rock, you'd expect to see, certainly you'd expect to see fossils. You know, the only reason I say in volcanic ash you might see some fossils is I think of Pompeii. There was enveloped in volcanic ash. People and things and houses were all buried and preserved by volcanic ash. So I'm not so sure you wouldn't find fossils in volcanic ash. But in any case, in sedimentary rock, we do find fossils. All right. So the deeper you go, the older the rock. And let's start answering some questions. Assuming there has been no geological activity, which means tilting, right? Folding, bending, flipping, right? Those things that we talked about earlier, because, you know, as we discussed in an earlier video, the tectonic plates could move and bend and shift. So you have to be careful when they're reading, the geologists have to be careful when they're reading these strata to make sure that they have plenty of evidence supporting the idea that the oldest rock is at the bottom. But assuming that there hasn't been any of that geological activity, which rock, A through O, would you find where would you find the youngest rocks? Where would you find the oldest rocks? The youngest rock at location 1 would be where? The youngest rock and location 2 would be which letter? The oldest rock in location 1. This is location 1 on this side, which would be sort of like, if we were facing north, it would be like the west bank of the flats, and this would be like the east bank of the flats, right? So location 1, location 2. State which layer at location 1 is the same age as layer M at location 2. Which of these is the same rock as M at location 2? This is M at location 2. Explain your reason for this answer. So why would you think that they're the same? Yeah, I think there's plenty of evidence for that. When you're looking at layers, it's really good to take a look at relative position, right? Because here we're talking about relative dating. So you have to think about relative position. So here's location M, or here's layer M, right? And here, where is it in reference to volcanic ash? So volcanic ash was an event, so a volcano erupted and laid down ash that happened at a specific time. When, who knows? But it happened here. So this stuff happened laid down after this eruption, this stuff before this eruption. This 2 times, right? However old this is even older. So you should be able to kind of layer down, discuss the layers in relative to the ash layer. You can talk about the type of rocks, right? So this has a certain kind of rock, right? This is a certain kind of rock. This has a certain kind of rock. And in this rock, in this particular type of rock, there is a specific kind of fossil. So on this side, there's a rock and a fossil, a certain kind of rock with a certain kind of fossil that's in a relative position to the volcanic ash, right? So when you're looking at this and say, explain your reason for this answer above, you should be discussing that reason in terms of its position, its location, M's location to the volcanic ash, the type of rock that it's made of, and the fossils that are found inside it. All right, the rock layers H and O are sedimentary rock. Explain why there are no visible fossils in these layers. There's H and there's O. H and O, and it's sedimentary rock. Why is there no? This question here is an interesting one. H and O. Why did H and O not have any visible fossils? I think the key word here is going to be visible. If we look at the organisms that move from here near the surface of the life as we know it, and we move down through the eons or through the ages, what we wonder then is life gets simpler and simpler. And if we think about the previous section of this workbook, we'd have to think about what came as we get simpler and simpler, what form do these creatures then take that lived so early on? So the earlier organisms were simpler. They didn't have the time to become complex. They didn't have the time to uh, develop the interdependent pathways and systems that we know today in the human body, the cardiovascular system, the digestive system. So as time went on, organisms were able to, through evolution, through the mechanism of evolution, were able to get more complex. You saw the endosymbiotic relationship and how that relationship, that the development of the cell itself, took time. So the other thing we have to remember about fossils, so that's one. And then two, the other thing we have to remember about fossils is that fossils, what is it that becomes fossilized, right? What part of the shark is made of cartilage, skin, muscle, blood, connective tissue, organs. What part of the shark becomes a fossil? Well, I hope you said, the hard part, the teeth, right? Those are the samples of the fossils that we've talked about up to this point for sharks. Is with sharks, it's the teeth. What other kinds of fossils do we see? Shells, right? There are imprints, right? Imprints of, and we've talked about the different kinds of fossils in the previous section. So there are imprints of soft tissue that we've seen, of skin and skin texture, and even of leaves. One would argue that leaves are soft tissue that rot, but imprints are slightly different. It would require some kind of structure, even then, some kind of hard structure in order to become imprinted. But in any case, you have shark teeth, shells. These are things that become fossilized more easily than things like the soft tissues of organisms. So when we look at fossils, they generally tend to be the shells, the bones, right? These are things that are more easily fossilized than let's say the skin, the hair, which is, and even feathers for that matter. And we saw that there were some feathers that were fossilized, but they were imprints. So they got squashed in mud, and that left an impression, and that impression was preserved. So it's different from becoming fossilized, but still they're fossils. They're a type of fossil. Fossilization in general, when we're talking about calcification, when you start to talk about the bones becoming stone or the wood becoming stone, you start to exchange material. You start to have a chemical reaction occur where the phosphates and the calcium carbonates take the place, the position that the biomolecules that used to make up that organism had, so that you get the same structure over time, but it's in stone. That takes time for that to happen, and of course the fossils can't. You don't want it to. There's a race between two different processes. There's that fossilization, right, versus decay. If the material decays, if it rots and becomes soil, for instance, before it can become fossilized, then you won't see it. So there's two possibilities that happened here. As far as why would there not be any visible fossils here in the O and H? Now, we have to assume that it is we don't have to assume it, it says it. These are sedimentary rock layers. Now, it would be unlikely if it would be very unlikely to find fossils in these layers if they were metamorphic or igneous rock, remembering that igneous rock is magma that cools. So magma is any fossil that's in magma is destroyed. It's been melted and turned into its pure elements and turned back into stone as it cools. So this material, so if it were igneous rock, which is cooling magma, if it were, then it would not be. We would not expect to see fossils here. If it's metamorphic rock, that's rock that could be igneous or it could be sedimentary. It could be any one of these. It gets buried in one of those subduction zones and gets melted and pressed and twisted and turned. Again, it would be unlikely to find a fossil in, like say marble, because it's been under a lot of pressure, a lot of heat. I don't want to say impossible because I don't know if there have been any fossils found in marble or any kind of metamorphic rock, but I would assume it would be unlikely. So fossils tend to be found in sedimentary rock, and this says it is sedimentary rock. So why are there no visible fossils in the layers? Again, I think the key word is visible. Well, if we think about the fact that these living things get smaller and smaller, and more simpler and simpler, right? And the first life started as a single cell and then started to become more complex as they become eukaryotes, as the eukaryotes differentiate into as they separate through evolution into two lineages, one the plant lineage and the other the animal lineage. As these single-celled organisms, these protozoans, then become multicellular organisms, and they further divide into yeast. You have all the different domains of life. As this happens, a large period of life, if you go back and look at the ages there, large period of life was of single-celled origin. There were no teeth or bone or hard material to fossilize. And they were very small. They were microscopic, single cells. Remember, we saw the fossils of the single-celled organisms called cyanobacteria, but those cyanobacteria, their fossils were what they created through their chemical processes, those layers of material that became fossilized as they produced it, the chemical product of their being, sort of like coral producing the reef. Coral are animals, they're soft-bodied animals, but they make a hard material made of calcium carbonate that we call a reef, right, a coral reef. So the hard part of coral, when you look at a coral reef, like when Dory from Finding Nemo, where she lived, that hard coral reef was made by a soft-bodied animal. So the hard coral reef would last. The soft-bodied animal would not be found as a fossil, right? So two possibilities here is, since we look at the simpler organism here of a snail shell or conch shells, then we have to think about, there's two possibilities for this. One, the first possibility is of no visible fossils, is that the fossils are microscopic. And they're the type that we've talked about with cyanobacteria, that are the products of their life, right? Their chemical reactions. The second is that there were no hard parts of the body to fossilize. So with things like jellyfish, you wouldn't expect to find a lot of fossils if the living organisms here, let me say this is 375 million years ago. If this was 500 million years ago, or something like that, where you had mostly jellyfish swimming around, would you expect to see a lot of fossils here? Now, there have been some fossils of jellyfish found, but they have been the imprint kind, right, where the jellyfish got squashed, and the imprint of that squashing left sort of like when you leave, exactly like when you leave footprints in the mud, the jellyfish, its body could have left an imprint in the mud, and that mud could have hardened. And in fact, there have been examples of this found in various places in the world. In fact, here is imprint of a jellyfish found in Utah. You can see the kind of, the traditional little rounded head and the tails, the tentacles, or whatever they're called, hanging down from the bottom of the jellyfish. The bottom line is that this is an imprint fossil, and they're not as common as you would find trilobites or shark's teeth or seashells, or those hard-bodied organisms that can be more easily fossilized. And so when we're talking about why there are no fossils in ONH, it's older rock, older than 375 years. It's closer to 500 million years. And if you think about the fact that about 550 million years ago is about when hard-bodied organisms started to show up in the fossil record, you expect to see that anything beyond 500 million years ago, 550, 560 million years ago, you wouldn't have any hard-bodied parts to fossilize, whether they be jellyfish or they be prokaryotes or they be yeast or some kind of fungus. These are soft-bodied at best and probably single-celled, so you would see microscopic evidence in the fossil record. You might find some imprints in the fossil record down here, but it's likely that these are really old rock and really early on in the development of the planet, so you would not expect to see many visible fossils. You might find microscopic evidence of life, but you wouldn't expect to see in very old rock visible fossils, meaning rock older than 575 million years ago or something like that. So state which layers at location 1 are missing at location 2. So here's the layers at location 1, which are missing here at location 2. Well, J is missing. The ones at location 1 that are missing location 2. J is added. It looks different there's an extra layer at J, but I would assume that B is like K and A is like I, and that C seems to be missing here at location 2. It's right above. There's a whole layer missing here. So which layer is present in location 2 and missing location 1? Again, that would probably be J. So J is missing here in location 1, and C is missing in location 2. Describe 3 methods of dating rocks. I think if you look back in the notes here in the reading, you'll find that answer. We've talked about relative dating, but you know what? I might as well go ahead and talk about different ways of dating rock. So, in dating the various rock layers, depending on what you want to do with the rock, why you want to have that date and what kind of information you're trying to gather, there's 3 different ways and what information is available to you. There's 3 different ways of dating a rock sample. So one is relativistic. The second The second is absolute dating. So this is rock dating, right? How old is the rock? How many millions of years? Relativistic dating, absolute dating. With absolute dating, you have radiometric dating. And then you have paleo magnetic dating. So those are the three general ways rocks can be given dates. So the relativistic dating we've already done, and you've seen it. This is younger, this is older, this is the older, even older, and this is the oldest. And based on various calculations, various estimations, you can say, well, this is so many millions of years ago. It takes about, it takes about 1,000 years to lay an inch of this sediment. So if there's 12 feet, then you have this many thousands of years. So that's what we. I mean, you can make all those calculations and estimations if you'd like, but that wouldn't really be very useful. The most useful part of using the rock strata is to say, well, this is the oldest and this is the youngest, unless there's some other example of tilting or folding or twisting or turning over. That's what we are dealing with in this particular area. That's relativistic. So we know these came before these. And so when people looked at fossils, by the way, they looked at, well, these are there's a lot more biodiversity here than there is here, and there is, you can tell a lot by what you're looking at, and just use relativistic dating without actually knowing anything about how much time has elapsed. Radio decay, radiometric dating is interesting. There are elements that are radioactive, and we know exactly how radioactive they are. In fact, our time as we know it, when you look at your Apple Watches or your phones, the time that you're looking at is the time that is calculated from an atomic clock. Is used to calibrate time. The element is cesium. And in fact, radioactive cesium has been calibrated and attuned so that its decay rate, which is constant, and that's what's interesting about radioactive decays, it's very constant. When you look at the overall decay rate of any amount of material, if you have a certain amount, let's say it's this amount, whatever that is, X, there is a specific amount of time that will elapse, and it's very constant, where half of X will be left. And that same amount of time, another half of X will be gone, and half will be left, etc. So we call this half-life. And by measuring the decay rate of any material, we can get an incredibly accurate measurement of time. And this is necessary to play, video games across the world with someone in China, where you pull a trigger and somebody else's tank goes down, or somebody else's plane goes down in China or in Japan or in India or wherever, or even just your neighbor. You have to be able to have incredibly accurate time measurements so that it all coordinates into a massive video game. environment. But that's also have this incredibly accurate time is necessary for GPS, so you can use your phones and know exactly where you are and where you're, how to locate when you go find your phone. It requires an exact measurement of time in order to be able to do that. Navigation on the high seas. In fact, one of the big great discoveries and great prizes went out to the first person to come up with a naval clock, a clock that could withstand the waves' motions and still keep accurate time. Keeping accurate time is incredibly important. And the most accurate timepiece we have is this idea, this atomic clock. Well, we can use the same idea of half-life and decay rate and the consistency of it. It's very consistent. Unlike the watch that you wind up that's based on springs, or even those that are based on solar batteries or the motion of your body, these timepieces are accurate, but they become less accurate over time. As time goes on, the device starts to lose time, and you'll have to reset it to some standard. That standard is generally today is the atomic clock, and using cesium. And we know that this is how accurate this is, that we use it today for most of our technology. Well, using that radiometric, that radioactive decay rate, we can also look at how old the rocks are. We can look at how different elements, how much of a different element is left in any one rock strata, and get a pretty accurate measurement of how much time has elapsed. Now, depending on what amount of radiation or what amount of time we think has passed and how much of the material, because obviously if every so often is after some time half the material is going to be gone, then you want to have either a lot of the material around and the time is short, or that time is very, very long, and no matter how much you have to start with, you're always going to have enough left over in the end to be able to measure how much time has passed by. So, for instance, potassium argon dating is looking at the radioactive decay of potassium 40 in rocks and minerals, and you can measure anywhere from 1,000 years to 1,000,000,000 years, because it takes a long time for potassium 40 to decay. Its half-life is pretty long, where carbon dating, when you're using carbon-14, non-radioactive carbon, the carbon that makes most of us is carbon-12. Well, carbon-14 is radioactive, and there's a certain percentage of it in the world, and as organisms stop taking in carbon-14, because as they stop using it, animals eating it, plants taking it in and making the sugars, that change, that amount of carbon-14 is going to become less and less over time. After about 70,000 years, there's so little around, it's hard to get an accurate measurement of time after 70,000 years. So you can go from 1 year to 70,000 years with radiocarbon dating. And you can find these in shells and bones and wood. Not fossil shells, bones, and wood, but shells, bones, and wood. In other words, organic material. That's where you're going to find carbon. Remember, fossils, the ones we find down here, have become phosphorus or potassium. They're made of minerals now. So there we'd have to look at minerals, how much of the minerals have been incorporated and how much of the minerals are left. So potassium argon, we can see, can go from 1,000 to 1,000,000,000 years. If we want to measure something like 500 million years, uranium lead is anywhere from 10,000 to 1,000,000,000 years. Fission track is 1,000 to 1,000,000,000 years. Luminescence is anywhere from 1,000 to 1,000,000,000 years. And depending on what material you're dating, does the stuff have potassium? Does the stuff have, is it made of feldspar, which is a mineral found in rocks? Is it made of quartz? Is this stone tools, pottery? You might want to use luminescence. If you're talking about uranium-bearing materials, you might want to look at electron spin resonance. If you want to take a look at stuff again with uranium, then you might want to have fission track dating. So all of these are very good for various applications, and this is what, this is how it's done here. If you want to look at something that's 100 billion years or more, you'd probably look at something like this, right? The chemistry of the age of volcanic deposits. Of course, 100 to billions of years, not 100 billion. We wouldn't be able to tell anything in 100 billion. So in any case, those are the different kinds of radiometric dating that we can use to measure the age of the rock. So when we say this rock is about 375 million years old, we probably are talking about radiometric dating, taking a sample and using one of these methods that we just discussed to determine the age of the rock. The same technology that we use on our phones for time, the same technology we use to navigate the world today, we would use to tell the time in how old these rocks are. The last of the type of dating that we can use to, again, give us some kind of absolute time scale, the age of a rock, is this idea of polarity of the Earth's magnetic poles. We call it paleomagnetic. So is 200,000 years in order to be 1 million years, right? So 2, 4, 6, 8, 1 million. So this is 200, 400, 600, 800,000 years ago, right? Up to 800,000 years ago, the North Pole was north. But about 800,000 years ago, it looks like the North Pole was at the South Pole, and the South Pole was at the North Pole. But at about 1 million years before that, so this is 100,000 years here. 100,000 years before that, the North was north and the South was south. But less than that, what looks like rocks that have been, I don't know, what would you call that? 50,000 years, 25,000 years went by, and then the North was south again, and that lasted for 2, 4, 6.5 thousand years. The North Pole was in the South Pole, and the South Pole was at the North Pole. The pointing, not the physical area, not the Arctic. The whole planet didn't flip. We're just talking about the magnetic field flipped. So that these flippings occur all the time. And in fact, I think I've read recently that the magnetic field of the Earth is flipping right now. So these rocks, the orientation of their particular magnetic field can help us tell a type of absolute time scale. So they're both absolute dating. The interesting thing is the radiometric dating gives you a range, right? So we're talking millions of years, where paleomagnetic gives you helps you constrain that, gives you a more precise age or date to the rock. The other interesting thing is that not all rock can be paleomagnetically dated, because in order to paleomagnetically date the rock has to be able to be a magnet. And of course that means it has to have some type of conductor in it, iron or something like that. It can't be made of silica, for instance. It can't be sandstone with no iron in it. Then it's not going to be very useful for paleomagnetic dating. All rock that can be dated paleomagnetically, though, can be dated or most rock that's paleomagnetically dated can be radiometrically dated, so that you can get a pretty good number as the age of the rock by combining the two. All right, so those are the 3 ways in which rocks can be dated. I hope this helped. All right, so in this last question, it's a pretty good puzzle. I'm going to let you do it. But understand that they're telling you that radiometric dating, the absolute type of dating that we discussed a little bit ago, radiometric dating is dated 3 layers, right? The first was 375 million years old. This fossil is 375 million years old. So this layer is 375 million years old. Volcanic rock layer D, this layer here, was dated 275 million years. So if we look at D, this is going to be 275. This one's 375, right? F is 375. So 175 million years went between D and E. And the let's see, layer D is 275, that's right. Oh, I said 275, it's actually 270. This could be accurate. You know what? Let me zoom in. Do 170 million years old, right? Where letter F is 375. F is 375. Okay? Now we go back, zoom in out, or zoom out a little bit, and take a look at what the next one is. B says is 80 million years old. So B is 80 million years old. I don't like that. Let's say 80 million years old. All right, so now we have some information that's going to allow us to date all the other rock layers, because we're going to combine this absolute dating that we talked about a little bit ago, radiometric dating, and if we had used paleomagnetic dating, with relativistic dating. So let's take a look at give the approximate age range greater than or less than or in between given dates, the rock layers. So if you know this is 270 million years old, and you know this is 80 million years old, what is this? Relativistically, in terms of D and B, how old is C? And A, how old is A? And how old is E? If you know this is 375 and you know this is 270, how old is E? G, where's G? G here, if you know how old this is, and how old is this? If this is 375, how old is G? L, so over here, if this is 270, what's this? And O is here. If this is 375, how old is this? And then therefore, how old do you think this is? So relativistically, you're going to date these given these absolute dates. This should be a fun little puzzle for you to do. All right, good luck.